Hello, and welcome to the next session in my webinar series on C++ Standard Template Library by example. Today, we're going to begin our discussion of C++ STL function adapters. And we'll begin by focusing primarily on the so-called binders, although I'll give you an overview of what function adapters are in general. So, as is our tradition, let me go ahead first and show you where you can find the code, and then we'll jump right into the analysis. So if we go over here and go to this website, this is my GitHub repository. If you look at the C++ STL S-09 folder, you'll find the 9.1 and 9.2 subfolders. And those will be what we're going to examine today during our walkthrough. So let's give a quick overview first of what function adapters are. By now, I think you've probably seen that C++ STL has a lot of adapters. So we have things like iterator adapters we've talked about. We have container adapters that we've talked about. And now we're going to talk about function adapters. And function adapters can be used largely to adapt functors so that they can perform composition and binding. So you can have fewer functors. You can reuse a lot of the ones that are already there and then bind them in interesting ways. And then you can also compose them together into so-called chains or trees in order to be able to have the output of one functor serve as the input to the next functor. And this gives you tremendous power to be able to combine and transform and manipulate functors with each other with certain values, like constants, for example, as well as with special functions. So there are three primary types of function adapters. There's binders, negators, and member functions / function adapters. And so the binders include bind first and bind second, and those are the ones we're going to look at right now. And they adapt functors by binding one of their arguments, either the first argument or the second argument. Negators include not one and not two, and these adapt functors by negating their arguments so that true becomes false and false becomes true. And then finally, the last type of adapter we're going to look at later, not today, are the member function adapters. And these include pointerfun, memfun, and also memfunref. And these adapters are used to allow functors to be used as class member function adapters. You can take things like pointers to member functions or pointers to functions and adapt them in ways that allow them to be used where STL algorithms expect to use functors. Something else we'll do along the way, too, in some of the examples, is we'll compare and contrast the use of functors relative to C++ lambda functions, which allow you to be able to write the code directly without having to create a separate class or reuse an existing class that's already part of STL's functor library. So let's go ahead now and take a look at some examples that'll make some of these concepts related to binders more concrete. So we're going to start here. This particular example is going to introduce the bind first and bind second function adapters, and then compare and contrast to see how they work in practice. And you'll see when I was first encountered with bind first and bind second, I was a little bit puzzled as to how they differed. So we're going to talk about how we can compare and contrast them, as well as how to use them in their common applications. So we'll start with demonstrate bind first. And you can see here we simply have a built-in array of numbers, 10, 20, 40, 30, 50, 20, 10, doesn't really matter the order. And then we compute ourselves a pointer to an int, which will then point to 1 past the end of that array using good old C-style pointer arithmetic, where we take the numbers array and we add to it the number of elements that are in the valid part of that array. So that reaches the end. And then we go ahead and use the countif algorithm. And we'll take a look at countif in a second. But what it's going to do is it's going to start at the beginning of that array, go up to, but not including the end. And then we're going to apply the bind first method to count the number of elements in that array whose value equals to 10. So let's take a look at some of the piece parts here. Here's the equals to functor. You can see it takes two parameters. It takes x and y, and as you might expect, it returns true if the values are equal, false otherwise. So that's the equal to part. Here's the bind first part. You can see the bind first part is going to take, first of all, it's a template parameter that's parameterized by the type of operation and the type that we're going to be using here, or a value we're going to be using here. And so we pass in the operation, and we also go ahead and pass in a const ref for the value. And you can see that bind first calls binder first, passing in the function that we're passing in, as well as the argument type parameter x in this case. And of course, the function is going to be whatever we pass into this thing, which in this case will be equal to. So that's basically what bind first does. And if we go and look at binder first, you can see that this is essentially going to be a class, as is often the case. There's a little wrapper method that deduces the type, and it's going to go ahead and take the appropriate operation here, which would be, again, one of the types that we pass in. That's a functor. Okay, so with that in mind, what we're doing here is we're basically binding the equal to method, which takes two parameters, so that one of its parameters will be the value in the range that we're iterating through, and the other value will be the constant 10. Now, just a quick recap of COUNTIF. So COUNTIF is what we're going to be using to do this call. And I've had some problems in the past getting CLion to find the COUNTIF method. So we're going to kind of do it the old-fashioned way by doing a search, and we'll eventually find the one that has the loop in it. And here it is. Here's the COUNTIF method that's being called here. As you can see, it's taking an input iterator and a predicate. And the input iterator is used to bound the range from first to 1 past the end, as always. And then the predicate is whatever we're going to be doing, which in this case will be applying the binder and the bind first binder. And you can see what it does is it walks through that range and it applies the predicate for each element to it. And every time the predicate matches, it increments the count by 1. And when we're all done walking through this, COUNTIF returns the count that we got, or the number of predicates matched. So the thing to notice here that's important is that bind first creates a functor, which in this case is going to be binding the equal to functor with the value 10. And that's the predicate that's going to be used here. So it's going to pass that in. And this basically converts equal to, which is a binary predicate, into a unary predicate by binding the constant 10 to it. And then that'll go ahead and return the number of values that are equal to 10. So let's run this code just so you can see what it's doing. And you'll see that in this case, there are 2 values in this numbers array that equal 10. So everything is fine. Okay, so that's bind first. Now let's go ahead and take a look at bind second, and we'll demonstrate how that works. And what's interesting, if you look carefully at the code, you'll see it's pretty much identical, except we call bind second instead of bind first. And if we take a look at bind second, you can see that here's bind second, and it creates a binder second. And if we go take a look at that, then you can see how bind second is defined. And it's going to take in the second argument of the 2, as opposed to the first argument, which is the one that was used for bind first. Now, what's interesting about this is if you run this code, and we've already run it, you can see that it returns the same result, except in this case, we decided just for kicks to search for the number of times that 20 appears as opposed to 10. So as you can see, if you look at the numbers array, 20 appears twice. So of course, we have the output saying there are 2 elements that are equal to 20. Well, at this point, you're probably scratching your head going, how does bind first really differ from bind second? They seem to return pretty much the same result each time. And so that's what I want to do here is I want to show you an example, which I've called contrast bind first and bind second, to illustrate the difference between these 2 binders. And it's not really clear, at least it wasn't clear to me until I saw an example along these lines. So here we're going to go ahead and have bind first. We're going to create a binder. And we can go ahead here and you can basically see what it's doing. That's what it is. It's creating a bind first, which is going to work on plus, but that's a little bit verbose. So rather than write this code, we'll just use auto. So we're going to get a bind first object. And then we're going to go ahead and do a bind second call here. And again, we could do this explicitly, and you see it turns into bind second, but that's also verbose, so we'll keep it with the auto. And the first bind first of binder is going to do addition with the value 10. So what we're going to do here is we're going to go ahead and say, I want to take this binder, and then I want to call it with 20. So what that's going to do is it's going to essentially add 10 to 20. And as you can see, the value is 30. No real surprise there, right? Same thing is true for the bind second variant here. So in this case, we have the plus binder, which will also add 20 to 10. And because addition is going to be commutative, a plus b equals b plus a, we don't really care which order things get done in, so we get the same value. So again, it still may not be clear how bind first differs from bind second. Now we're going to see how they differ. So down here, we're going to define ourselves a new pair of binders, which is going to use the minus operation this time, instead of using the plus operation or the plus functor. So in here, we're going to have the minus functor, which is going to be bound to 10 with a bind first, and then we're going to use bind second to bind minus to 10. So now we have two new binder objects, which are binder second objects. So if we go over here and we turn this into the actual code, you can see it turns into binder first and binder second. Just for kicks, let's do that just to be complete. So you can see here how these are turning into binder first and binder second objects, which are verbose, so we use auto. And then we're going to apply minus, and now you can see the difference. So when you do M1, that's going to go ahead and bind 10 as the first parameter, and then it's going to go ahead and subtract 20 from that. So of course, 10 minus 20 is minus 10, which is what we get here. Whereas when we do this with bind second, you get 20 minus 10, which is 10. So now you can see the difference when you have non-commutative operations. It makes a difference as to whether you use bind first or bind second. But when you don't really care, then it doesn't make a difference for commutative operations, or as we use them up here in these countif contexts where we were using predicates. It doesn't really matter in that case because we're just checking for equality. Now, if we were checking for some other relationship like greater than or less than, then it would make a difference whether we used bind first or bind second. So hopefully that gives you a little bit better understanding of binders. Now, this particular example focused on using binders in the context of built-in types like int arrays. And so the next example we're going to look at is going to show you the same concepts, the same capabilities, except this time we're going to look at it in the context of STL sequential containers, like in this case, vector. So this is going to show bind second. We could also show bind first, but I'm showing bind second. And it's also going to demonstrate the use of a C++ lambda function in lieu of using binders in the context of various STL algorithms, some of which we've talked about before, but I'll go through them again. So as you can see down here, we're going to define ourselves a vector of doubles, which we initialize with an initializer list. And then we're going to define ourselves a field called, or a variable called factor. Probably should use auto here if I can get away with it. And then what we're going to do is we're going to use the transform algorithm. And if you recall transform, it's going to go through the vector, and it's going to go through the entire range from beginning to end. And it's going to apply this unary operation, because this is the 4-parameter version of transform. It's going to apply this unary operation, which we get by using bind second with the multiplies binary functor and the factor that we defined up here. And in this case, I probably could say const auto factor because I'm not going to change it. So that's just making it more clear that that's a const. It didn't need it, but it helps to make your code more clear what's going on. Now, where does this result get stored? We're going to put it back into the vector itself. So we're basically going to multiply all the contents in my vector by the factor. And so what we'll end up with is a modified set of my vector elements that have been multiplied by 33 1/3, which of course is the old speed of LP records way long back in the day. Okay, so we're going to do the transformation. We'll end up with the multiplied contents in place. And then we go ahead and print out the results. The next thing we're going to do is then we're going to go ahead and use the countif algorithm, which we've also talked about before just a minute ago. And we're going to go through the vector that's been multiplied, and we're going to find how many values in there are greater than 1000.2. And once again, we're going to use bind second. And in this case, rather than doing bind second for multiplies, as we did up here, we're going to use bind second with the greater functor. And I'll quickly go through these code. We'll look at the code in a second. I just want to give you the big picture view first before we do some diving into the implementation. So what this is going to do is it's going to count how many values are greater than the value object that we have here, the value variable. So that's what we're going to do. And then we're going to print out the number of elements that are greater than that value. And then the final thing we're going to do is we're going to use the find-if algorithm. And that's going to start at the end of the vector, because we're going to use r_begin to start at the end. And then we're going to go to the beginning, which is rn. So r_begin starts at the end, rn goes to the beginning. So we're going to iterate backwards. And this time, just for kicks, we're going to use a C++ lambda function rather than using any of the predefined binders or arithmetic operations like multiplies or the relational operator like greater and so on. So in this case, we're going to go ahead and find the last element in our range that's value is greater than 1200.4. And you can see how we do this. This is a lambda function. All you really have to do is you have to provide the type that's being passed, which in this case, of course, is a float, because it's a vector of float. And then we just write the code in line. We just say return f, which is the parameter, greater than value. And if that's true, then it'll go ahead and match it, and it's going to start from the end. So we'll see if we get a match. You'll also notice that we have to pass in the parameter from the scope. So the scope here is the local variable value, and we have to indicate to the lambda that that value will be passed into the context of the lambda function. Otherwise, it would be invisible. If we take out this here, then you can see it's basically going to say something like can't implicitly capture the contents of value. And this is what's called the capture clause, where you can put in the variables you want to have captured, in this case by value. You could also do them by reference if you plan to change them, which we don't do in this case. We'll talk about passing these by reference in another context. So if we're lucky, or if not, if we're lucky, if we find a hit for here, that means that the iterator that we get back from find_if is going to be not equal to the end, or the r_end in this case, of the vector. And in that case, we're going to go ahead and print out the last element that's greater than the value. So let's run this code, and then I'll walk through some of the implementation details for you. But I want you to see what it does first. So over here, you can see that we took our original vector and multiplied everything by 33 1/3, and then we printed the results out, and that's the first line here, just the results of multiplying it by 33 1/3. Then we go ahead and we find the number of elements that are greater than 1000 and 0.2. And in this case, we use the greater relational functor, and we turn it into a unary functor using bind second, which is the binder. And as it turns out, there are 3 values that are greater than 1000.2, and you can see that they're the last 3. Doesn't really matter which ones they are. Probably need to put an equal sign here just to make it more clear what's going on. And then the final thing we do here is we go and we search backwards in our vector using r_begin and r_end, looking for any element that is going to be greater than 1200.4. And of course, we find that right away because that's the very first element in the end of the vector, which is 1681.65. So that's what gets returned from the iterator from find_if, and that's what gets printed out here in this cout statement. Okay, so that's the result. Those are the results. Let's go take a quick look at some of the code. We've looked before at the implementation of some of these things, but just for completeness, in case you hadn't watched all my other videos, here's the transform algorithm. And you can see that transform is a very interesting algorithm. It takes several different types of type names in its template parameter list. It takes an input iterator, an output iterator, and a unary operation. This is the 4-parameter version of transform. There's also a 5-parameter version as well that takes binary operations as opposed to unary operations. The actual transform algorithm itself takes an iterator range from the beginning to the end. That's what we're going to iterate through, and an output iterator where we're going to put the results. And then we also have a unary operation, which is a predicate or a functor in this case, or a composed bounded functor. And then down here, you can see that the actual algorithm goes from beginning to end, and every step along the way, it calls the unary operation, which is the binder in this case, which is adapting, in this case, the multiplies method, and we go ahead and apply that on each element in the range, and we store the results into the output. So that's basically what's going on under the hood. But of course, because of the fact that we're using the binder here, what we're passing in is actually a sort of a chain of functors. So binder is going to, as we saw before, bind second is going to take the functor that's passed to it and a value, and it creates a binder second object. And then the actual functor we pass it is the multiplies functor. And you can see the multiplies functor does sort of the obvious thing. It takes two parameters and multiplies them together and returns the result. And in this case, what it's doing is we've bound it such that the factor is the second factor. It is the second parameter passed in, and that will then be multiplied by whatever happens to be in the buffer, in the range rather, that we're iterating through with our transform algorithm. So you can see each of the elements in turn gets passed to that unary operation, which is, of course, the binder, which encapsulates the multiplies functor. So this is really cool, and I think the key thing to keep in mind here is that we're composing together these functors in order to make them conform to the signatures expected by the STL algorithms, in this case, the 4-parameter version of transform. We've looked recently at COUNTIF. I'm not going to repeat that because we just looked at it. Same basic idea here. The main thing I show you is the greater functor, which, as you can imagine, takes 2 parameters. It's a binary functor, and it returns true if the first parameter is greater than the second one. I think that's pretty obvious from the name. And in this case, we're going to bind the second value to be 1000.2. So it's going to see which elements in that range from beginning to end of the vector are greater than that value. And then the final thing we're going to look at here is find if. And I think we've looked at find if before, but here's just a quick recap of it. So you can see that find if is going to take a range from beginning to end as an input iterator and a predicate, and it's going to go ahead and see if it can find the first predicate match. Now, this is another one of those places where C-line is getting confused. So let's go see if we can find the find if algorithm that actually has the implementation in it. Let's see, not quite yet. You can see there's a lot of places where find if is actually used to do other stuff. It's kind of a workhorse algorithm in STL. And here we go. We finally found find if. I think it's looks like it's the very first one. I probably should have started searching from the beginning. So as you can see here, find if takes an input iterator and a predicate, and then it takes as a parameter the first in an iterator to the beginning of the range and an iterator to one past the end of the range. Those are input iterators. And it takes a predicate, and it goes ahead then and searches from beginning to end. And whenever the predicate matches, then we're going to go ahead and return. And so that's how we're going to get it to work. And of course, the way it's going to work here is we're going to actually use the rbegin factor method on the vector, so that it's going to give us a reversed iterator that actually starts at the end. So rbegin gives us one that starts at the end, and rend will continue. It'll give us back an iterator that will be used to bound the search when it reaches the beginning. And so that's basically how we're going to use it in this particular case. So that's really what I wanted to show you today. I think you can agree that there's some really cool stuff here with binders. Binders are very powerful. They get used all over the place in STL, and we'll show lots of other examples of binders and functors when we talk about the negate function adapters, which we'll do tomorrow. And I'll also continue to compare and contrast the use of the functor-based approach with the approach that uses lambda functions, because I think it's important to know how they differ. And then we'll also talk, of course, about when to apply one versus the other. As a general rule of thumb, if you have built-in STL functors that you can use together with binders and negators, that's a very fast way to write the code, because it's already there and it's pretty intuitive and you don't have to think very hard about the syntax. Conversely, if you're writing code where you're creating your own computations that don't fall nicely into what's already packaged into STL's pre-existing functors, then you might want to consider using lambda functions, especially if it's just a one-off type of thing that you're not going to be using over and over again. But we'll see that as we get a little further into this in subsequent sessions in my C++ standard template library by example series. So if you like this content, please feel free to like and subscribe, and also you're welcome to follow me on Twitter. So thanks very much, and I'll talk to you soon.